Okay, now let's consider the capabilities of a radar to measure velocity. This is based on the Doppler effect. The Doppler effect is well known in physics and allows the radar to observe the radial speed of targets. So actually, Doppler is actually a narrowband concept. So it can be applied to most of radars, but actually what happens is that the radial velocity between target and the radar induce a time dilation phenomena or change in the echo signals, which can be interpreted in terms of a frequency shift, but actually it is a time dilation process. So to understand this, let's consider now a small animation here. We have here first a static situation. The target is not moving at this, in this case. We have the radar here at the left. We transmit a pulse. The pulse eventually reaches the target. I use here a special shape of the pulse in order to see the symmetry of the pulse. This could be a radio frequency pulse or any other signal. Okay, so now, according to the duration of the pulse, this has a space duration here, which is the speed of light multiplied by the time of the pulse. Now, T, capital T, now is the duration of the signal we transmit. Okay, we reset our clock here. We put the clock at 0 when the leading edge of the pulse, which is A, reaches the target. Okay? Now, after a while, after a short time, delta t, actually the trailing edge of the pulse is abandoning the target. So now this is the illuminating pulse. It has been, is continue its way here at the right. And okay, an echo signal, which is here depicted in blue, is now back propagating towards the radar. Now we stop the clock here, and this delta t parameter indicates when the trailing edge is just leaving the target. Now, because the target is static, you could see here both signals, the one that is continuing its travel and the one which is reflected, which is the echo, have the same shape. And actually, the echo duration is exactly the same as the incident pulse duration. So in this case, the echo is just a replica of the illumination. Now, let's consider a moving target in this case. We repeat the experiment. So now our target is moving towards the right side of the slide at a certain velocity, v. So we, as before, we reset our clock t equal to 0 when the pulse leading edge reaches the target at this point. Okay? Now, after a small time, the trailing edge of the pulse actually abandons the target. Trailing edge is B here, now it's just touching the target. But notice that compared as in the previous case, this happens with a position of the target which is shifted towards the right. So the signal has traveled a small amount of range, additional range with respect to the previous situation. This means actually pulse B reaches the target at a later time. So delta tau prime here is slightly more compared to the static non-moving case before. Now, the distance which has been traveled by B from t equal to 0 to delta t prime, it is this one here. From this point, which was t equal to 0, to this point at t equal to t prime, delta t prime. So in this case, we can measure the space which has been traveled by B from this situation to this delta t prime situation in two different ways. We can first measure the distance from the space traveled by the signal from this position at t equal to 0, which is from this position to this position. This is Ct plus v delta t prime, because in delta t prime the target has moved to this position. And we can compute delta r prime, so this range, in a different way, from the time traveled by the signal from t equal to 0. The time is delta t prime multiplied by c, that's the range which has been traveled. Then, comparing these two equations, we can obtain the parameter of the time traveled by the trailing edge B, which is capital T divided by 1 minus the ratio between the speed of the target divided by the speed of light. So this is a relativistic computation or analysis of the situation. Now, the echo duration, T prime, you can notice it has been expanded. So the echo shape is similar to the incident shape, but the time scale has been dilated, this has been changed. Then if we compute T prime, now we can add the different, for example, from the origin towards the right or towards the left, we can add these two parameters and we obtain what is the period. And the new period is actually this new expression. It is actually a factor of the original one. This factor can be higher or lower than 1 depending on the velocity of the speed sign. So in this case we have analyzed a departing target is opening from the radar, then the echo period or duration, it is larger than the original, but if the target moves towards the radar, it will be shorter. Now, because this results in a time dilation, this means that when we transmit a signal, which is here denoted with SE of t, the echo, it is actually a delayed version, but also a time-scaled version of the incoming signal. Of course, this change is very small in practical situations because the speed of the targets, in real cases, are much slower than the speed of light. So this ratio of time dilation is very small, it's almost 1. So, for example, for a speed of 1000 meters per second, this time dilation is 1 minus 6 to the 10 to the minus 6. So it's a really small change. So for narrowband signals, when we can define the transmitted signal with a carrier here, an amplitude and a phase modulation, the received expression of the echo is this one here, when we have this time dilation here factors applied to both the modulation and the carrier. For short pulses, the impact on the modulation part is very small, it can be neglected. But because the carrier is extremely large, even for 1 gigahertz is 10 to the power 9, then what we have is the impact of this time dilation is mostly on the carrier. So it alters the carrier significantly. And this can be measured as a frequency shift, which is the definition of the Doppler frequency. The Doppler frequency is a frequency shift, an apparent frequency shift, which has been induced by a time dilation process due to the relative velocity between target and radar. So in most of the situation, almost 100% of the situation, you can ignore the time dilation and you can just concentrate on the Doppler shift of the carrier. The expression here, resulting expression is very simple, it's proportional to the speed, and you have to multiply in a monostatic case by -2 over lambda. The minus sign means if the velocity is positive, which means target is increasing range, the correction in Doppler is negative, which means the signal comes at a lower frequency than the original, compared to the original. 100 meters per second at 1 gigahertz results into an audible frequency Doppler, which is 600 hertz approximately. But remember, Doppler shift is a narrowband concept. So actually what happens is actually a time dilation process. So if we have a very wide band signal or a very long signal, it is much better to analyze the impact of the radial velocity in terms of the time dilation instead of the narrow band approximation, which is just a Doppler shift. Take a look to a reference, Titan Collin reference paper, which is actually mentioned at the end of the radar course, which is actually a good example of you must not forget the actual process is a time dilation. It's not only a frequency shift. Now, how can we use the Doppler shift phenomena in order to measure the velocity of the target? Well, that's very straightforward. For example, let's build a radar to measure the speed. You can do this with just an oscillator. We transmit this power, no modulation at all. We just transmit a constant carrier. Then we obtain an echo. If the target moves, the echo actually has a Doppler shift, which can be obtained with a mixer, which actually compares the original frequency with the incoming echo frequency here. We obtain the difference, and that's the Doppler frequency here. We can amplify, we can analyze the frequency with a frequency counter, and then we obtain the speed of the target. This is what low reinforcement radar in motorways is being used nowadays. Now, with a continuous wave radar, can we measure range? Well, the answer is yes. We can still measure range by transmitting continuously, but we have to introduce a mark or some time reference in the signal. If we cannot pulse the radar by definition, because this is a continuous wave system, we can still introduce a modulation. And something we can do is to use a frequency modulation, for example, a linear frequency modulation, like in the chirp, but without doing any pulse. So we continuously change the frequency of emission following, for example, this triangular modulation pattern. So this is a plot of the instantaneous frequency which is being emitted by the radar. Then we transmit this signal, and we receive the echo, for example, from a static target at some range separation from the radar. The range separation translates into a delay, and this delay actually transforms into a replica of the instantaneous frequency of the echo, which is actually shifted in time. And if we compare both frequencies, as in the previous case with a mixer which obtains the difference of frequency after a low-pass filter, we obtain a beating tone here, which it is mostly constant frequency, apart from the change of sign in this crossover region here. The beating tone is mostly constant, and this beating tone actually is proportional to the range of the target. This is actually the product of the slope. This term is the slope of the modulation. This term here is just the delay of the target, and we obtain beating tone proportional to the range with a constant factor here, which depends on the modulation parameters of our radar. And now the resolution after, for example, FFT spectrum analysis of our echo signal, the range resolution actually is once again c speed of light divided by 2 times the bandwidth. The bandwidth here is the excursion of frequency delta f. So if we use a very wide excursion in frequency, we can obtain a very nice, very thin resolution range up to centimeters in microwaves. This is the front end of a continuous wave FM radar. When you see here the transmitter section here, and the local oscillator is actually applied here into the receiving chain when we have the 2 mixers for the IQ detector. So this is a small radar front end that can be integrated in the small platforms.